It is? I gotta go check it out. What?
No.
It's not? Okay, I'll wait for it. Alright. Here we go. This joke will change your life.
A bear that's white and lives in the North Pole.
No.
It's a bear that you make.
It's a bear.
Polar equation.
It's just a rectangular bear, guys. After a change in coordinates.
Wait, what's a rectangular bear?
Oh, okay. Sorry to subject all of you to that. All right. Thank you, Dinesh. Appreciate that pity laugh in the back. Okay. All right, so let's talk about polar systems today, and that's probably what you would expect. It's graphing two polar equations at once. We're trying to find intersections. We're trying to find out the places where that satisfy simultaneously both polar equations at the same time. This is fun. This is fun. This will take some good skill with graphing these. That's going to be good for us to be practicing, even though this is not a skill that's on the quiz on Thursday. Graphing is, so every time we're going to set one of these up, we're going to be graphing them, which will provide you with some good opportunity for practice. I think you'll be glad for that. All right, so here we go. R equals 4. What? That's not one of the equations that... Oh, you do know how to do that one, though?
Yeah, you draw it on the fourth circle. It's like, just like universal. It's just a circle.
All right. There we go. There's the equation R equals 4. Here's the equation R equals 4 cosine 2 theta. Let's practice graphing that. What is that again? What kind of animal is it first? It's a rose curve with petals of length 4. How many?
2.
4. 4. Pointing in which direction? All you need to give me is 1 at least first. What's one of the petals pointing in? Don't we get one right away at 0? Okay. We get a petal of length 4. Okay, and then the rest are all 90 degrees apart here. So, are you ready? This is fun. We like drawing these.
Mr. Chase, how are you so good at drawing those? It's not that hard.
I don't know. I messed up right when you were saying that, actually. Why'd you mess me up? No, it's all right. I have done it a few more times than you, but okay. So maybe this is the end of the story, right? We're just like, okay, 4 places, and we should just name them and just move on to the next problem. But we need to like really slow down and think about this a little more, and also keep in mind that when you're solving a system, in fact, actually graphing is usually not the place you go first. Let's actually do the algebraic approach here and solve this algebraically. So let's solve the equation by setting them equal to each other. Isn't this what you would do if you were in rectangular coordinates? You set them equal to each other and find the places where this is satisfied. So go for it. When is cosine 2 theta equal to 1? Well, that would be true when 2 theta is equal to 0 or 2 pi or an infinite number of other things. And then when we divide through all of those things by 2, we get 0, pi, and on the interval of interest, those are all 0 and pi on the interval of interest. Okay, so that sounded really good, and I think you're all with me. But there's a snag. That's only these points. That disagrees to some extent with what we've just been talking about up in the picture. So there's something to be talked about here, right? There's a discussion to be had. I definitely want to start listing the intersection points here. So let's do that. Intersection points for r, 0 for theta, for pi. But what about these other places? Talk with your group for a second about why that's happening. What's going on here and here. Talk amongst yourselves. Do I need to keep adding some more here? What's going on? All right, what'd you say? What'd you say? Kevin knows?
Kevin.
Go ahead, Kevin.
I'm kidding.
We all want to hear from Kevin. Go ahead. Why is this happening? Why don't we get the other two, or what's going on there? Help us out here. Is that a hand arrow? Jasmine. Oh, now you're ready?
No, it's fine.
Pi over 2 times 2 equals pi, which is one of the animals. So is that one?
Root 2 times pi.
No,
Pi over 2 times 2. Pi. All right, we're going back to Kevin. Oh, Suri, go ahead. She's the one calling Suri everybody else. So go ahead, Suri.
That's the same answer as mine.
But his answer wasn't very complete.
Yeah, I know.
Could you do
We
it
discussed
better?
the same answer.
Okay.
Same answer.
All right, go ahead, Dave. Because why? Say it one more time. Because of something about the -4. Yeah, I think that's fair. I mean, if we're at pi over 2, if you plug pi over 2 into the blue equation, you get 4. But if you plug pi over 2 into the second equation in red, you get -4. There's never a time. Then you get these two as the answer, and not these two. You're right. Yeah. So we do still want to we still want to say something about those. We'll call those common points because we want to acknowledge that the two graphs do occupy those two spaces on the graph at some time. So I don't know. What do you want to call those? 4 pi over 2 and 3 pi over 2. But it's also kind of a little bit of a lie because there's never a time when you plug pi over 2 into both equations and you get 4. Right? It's not true. In fact, if you plug it in here, you don't get 4. So, but we'll still call them common points. In fact, actually, all the intersection points you might also call common points as well. But I won't be too nitpicky about that. I mean, I guess technically there are 4 common points if you want. All right, so let's go to the calculator. Get your calculator out, and let's plot this on the calculator and see what we can see. You've got a cool new calculator. You can do it in blue and red too, just like I have.
Whoa.
Do it simul mode. We're going to do simul mode, simultaneous graphing, both equations at the same time. We will use the ball. You gotta use the ball. And okay, what else do we need? So I'm going to try and enter this up here. What do we have? 4 and 4 cosine 2 theta. Window 0 to 2 pi, but let's not graph it yet. Here we go. Okay, let's not. Oh, don't know what you did. What? Josh, no. All right. So the thing you're gonna do is let's think about what's gonna happen. Let's predict what we're gonna see. The graph is gonna go like this. Watch. 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 Right. Right there. Ready to see that? And at the same moment, notice that those other places they were opposite locations. Here we go. Oh, whoa, 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 whoa. Oh, this is so sad.
Yo, mine's oh, are you
I'm gonna need to do some repairs. 1 second.
No. Can't be doing on your widescreen.
Bear with me. All right, here we go. Whoa, whoa, wait. All right, so boom, right there at the beginning. Look at this. Look at this. Denied. And then look. Okay. Boom. Denied. And then boom. Right? So do you see that's what we promised would happen? That's what we promised would happen. Next problem.
Wait, did you guys use our calculators to calculate this on the test?
I don't remember. Did we need the calculator just now?
No.
No.
I kind of did.
Oh, did you? No, it's I think the test we have for this unit is all non-calculator. Where's this too?
Those are all harder.
Is it? I actually prefer non-calculator. I think it's, calculators are annoying.
This person who got to use the ball guy. He's so excited about using the ball when
Oh, yeah, well that's true.
Yeah.
But I don't know, calculator slows you down.
what? Actually, speed me up.
What is this guy? 1 plus 2 sine theta? What kind of curve is that?
Oh, that is
Okay. Maximum R value is 3 occurring in what direction? When theta is, when is sine theta at a max? What angle? 1, 2, 3. Yeah, in the pi over 2 direction. What happens in the 0 and pi direction for this guy?
They go like
Just 1 in both those directions. You get the kind of, that's 1 wide. And what's the minimum R value? We didn't say it yet. -1. So does this go through the origin? Yes, by the intermediate value theorem. Right? It does, goes from, if the range is -1 all the way up to 3, then yes. So what does that -1 tell us? That's the size of the inner loop, and there is one, we should say. And it occurs in the 3 pi over 2 direction if you want, but it's up here though, right? So let's graph that as best we can here. Something like that. That's not my best graph. I'm going to try again. That's a little better. There we go. I don't know. It still needs work, but whatever. In red now, the second equation, what kind of graph is that? Also another limacon. Max R value? Yeah, 5 when sine theta is -1 we achieve. So when is sine -1? At angle 3 pi over 2. So 1, 2, 3, 4, 5 in the 3 pi over 2 direction. Just check us on that. If you plug in 3 pi over 2 for theta, do you not get 5? Yes, you do. What's the minimum R value here? 1, and that happens in the pi over 2 direction. And if sine is, again, if sine is 0 or pi in these 2 directions, you get just 1, 2, 3. All right, so we're doing well here. Again, that could have been maybe better, but we'll go with it. Okay. Okay. Well, once again, let's go to the algebra 2. Already we have a sense that maybe there are how many intersections? At least visibly. Looks like possibly even 3, 1, 2, and then that one in the middle there maybe. 1 plus 2 sine theta equals, work it out guys, 3 minus 2 sine theta solve. We're looking for angles that have a sine of a half, I guess. Where are those? Five or 6, yes, and 5 pi over 6, and others, but just those if we're on the interval 0 to 2 pi. That's good, because that kind of confirms what I'm seeing in the picture. In fact, this is a good evaluation of how well I drew my graph. I get full marks for that one there. Come on, guys, look at that. That was luck. Okay, and over here, it's not bad. I mean, it could be worse. Could be worse. We'll pretend that it did. Okay. So we got some intersection points. We're missing the one that we think we thought we had in the middle there. We were feeling good about that, but not so much anymore. So we'll write down our intersection points as something pi over 6 and something comma 5 pi over 6. Do we actually calculate what it is? What happens if you plug in pi over 6 to one of or both of the equations? You get what? Sine of pi over 6 is 1/2. Yeah. And if you plug 5 pi over 6 in, you get 2 as well. I'm seeing that on my picture too, but I just want to confirm. And then we have still a common point. Like I said, these are also common points that we just came up with, but we want to name that point in the middle somehow maybe as well. What do you want to call it? Just 1 maybe, comma pi over 2? Sorry, Aiden, go ahead.
If we're like on a test and we're asked to graph it and find the intersection point, like we draw the graph first, intersection point, and we like that. Like, should we like completely draw the graph?
Not if it's
I mean,
unless
like,
it's really terrible. You are doing it in pencil, so if you just need to adjust it a little bit, you could. The important thing is, if you do the algebra, if you get these answers, I'm probably going to be a little forgiving. It should be like relatively right though,
Yeah, but
Yeah.
it's.
If it was a little off, they'd be forgiven. Yeah.
Well, the common point is just based on what you're looking at.
Yes, right now the common point is based on. That's a good point. Maybe that's the only level to which our analysis. Okay, fine. Yeah. That will be the only level to which our analysis rises. But if you want to think more deeply about how to do that without finding, you need to maybe do a little more algebra to think about that. But yeah, our analysis will be based on the graph. I'd like you to graph it as well. Which is not like entirely satisfying, I realize, but yes, whatever you say. All right, here we go. 1 plus 2. Oh, that is not how you enter stuff on here. Plus 2 sine theta. And 3 minus 2 sine theta. All right, let's watch this thing go. Ready? Boom, boom. And denied. And wait for it. Boom. And then, the rest is less interesting now. There's the denied right there. Denied. So we see it all happen. Great. Doesn't this remind you a little bit of our discussion about parametric lines and whether they intersect or not? Like, there's this kind of extra demand that they not, like, do they intersect at the same place and time? Like, that we have that kind of, it's not really time here, but it is similar in terms of the discussion we're having. Are we having fun yet? This is good stuff, right? Man, I love this. Okay. What else do you want to say? I don't know. This is just a fun problem too. In some ways, so one thing I should say too is this is somewhat unrelated to what we were just doing. I acknowledge, but in some ways, my goal for today is to do some things that, the reason you do polar systems is partially in this too. This is not polar systems anymore. I'd like you to think about it. Especially in the name of calculus for next year, one of the things you'll be doing in calculus is we'll be finding the length of polar curves, we'll be finding the area inside polar curves, and a lot of times what they'll give you is here's a polar curve, here's another polar curve, find the area in between them, and that involves finding intersection points and analyzing when this loop is created, for example. Find the area inside this petal. Well, you'll have to know what values to use to create this petal. So I don't know. I do all of this in the name of calculus as well. Also because it's interesting in its own right. So see if you can solve this problem while I pass out this. Go ahead, figure it out. Another way of asking is asked a little weirdly, I admit. Another way of asking this would be how did I graph this on my calculator, right? What restrictions on theta did I use to just restrict it to one petal of this guy? You can figure it out. 5 that I'm tapping out right now is right here. And it will be due on Wednesday. I will talk about it. You can do it tomorrow. No, but it's on a worksheet though, so you might be doing, you might like do it on the bus or in chemistry class tomorrow or something. At lunch, right? No, I know you don't ever do that. I was talking about other people. So you understand the question I have up here for you? You're trying to create this pedal. It's a 5-petal rose curve, right? Petals of length 200. So certainly you would know that this pedal is part of the picture, but it's only a fifth of the picture, kind of. So what values of, if you were to graph this on your calculator, put this in Y1, if you go to your window, what theta min and theta max would you put? Is really this question. In order to see only this. Figure it out, and when you think you have it, tell me and we'll try it up here. You got it?
Negative pi over 10 and pi over 10. Yeah.
Wait, I'm not ready. Is there purple on the calculator? Because I want it to be purple. Magenta? There's magenta. Why is there not purple? Is there purple? Alright, we'll do magenta. Alright, we ready? Alright, I got it in magenta. That's the best I can do. Window, you say negative, what'd you say? This is the moment of truth. Are they right? Let me first hear why you said that. Person who said that. Francis, go ahead.
Or both me and Katie.
Yeah.
Well, there's going to be 5 petals.
Okay.
Each petal is going to take up 2 pi over 5 of the graph.
Okay.
And so this one stretches from partly below, or it's partly negative and partly positive. And so when 2 pi over 5, or pi over 5 is evenly divided between the positive and negative section of negative 5.
Yeah, your graph's in 0 to pi is what this graph's in. So you're looking for a fifth of that, but then it's split. Okay, I think I don't know. Let's just see what.
That was a terrible explanation.
I just think like whenever equals 0,
It does appear that you're right. That is beautiful. Okay, look at that. So negative to positive pi over 10. Katie, say your way again.
Oh, I just kind of like, so basically I know that like the cosine of pi over 10 will always be 0. So I try to make like that 5 pi equals pi over 2. I mean 5 beta equals pi over 2.
Pi over 2.
And I mean beta equals pi over 2.
Okay, I'm with you. I'm with you. Okay, so we want 0 to be the R value. And that happens, you're saying cosine is 0 when theta is pi over 2 plus or minus. But we're talking about 5 theta here.
Yeah, that's fine.
I'm with you now. So alpha and beta are negative and positive, pi over 10. Or there are there are an infinite number of correct choices, I guess. I think it's worth talking about how you might do that. Remember, just put in math terms what you really mean in life. If you want to be like, when do I get this pedal, or when does this pedal start and stop? What we're really asking is like, when is R 0? Right? Isn't that R equals 0 corresponds to when it starts and stops? So just solve that equation. When does this equal 0? I don't know much more to say. Give these a try. Some of them are a little trickier than what we just saw in terms of the systems we solved. Some of them are about the same. So have fun. Again, for those who didn't hear me say it, this will be not talked about or checked until Wednesday. Okay? Tonight, your goal is to bring something of great substance tomorrow to the conversation as we think about our drafts. And that's your only obligation tonight. Tomorrow, and then Wednesday, we'll check this homework and go over it, and also begin something else. Thursday's the quiz on homework 1 through 4. Other issues, questions, comments?
How's your weekend?
Eden, that's very nice of you to ask.